Let's have another solid figure, and in this problem, we are required to determine the dimensions of the largest thin cylindrical can that can be placed inside a spherical balloon. So, wag nyo nang isipin kung paano nangyari tong tin can na ilalagay sa spherical balloon. Posible na baka may relief operation and then kailangan dalhin natin yan dun sa mga mabawa na sa lantahan ng bagyo. So, kailangan ilagay siya doon sa yun, sa loob ng balon na yun. Syempre, hypothetical lang naman to. But that's probably how this works, and what we have to do now is to illustrate that. So I'll be drawing the cylinder na i-enclose natin sa spheres. So basically itong cylinder na to, or the tin can na kung ano man laman nun, is basically inscribed. So inscribed siya sa ating sphere. Kaya i-require natin is ano ba yung maximum volume na pwede inscribe natin sa loob ng isang sphere kung meron tayong isang cylinder. So ito yon, ganda. And then we need to have the sphere. So itong sphere na to, so mapapansin nyo, dapat perfect siya, circle as much as possible. So yan, okay. And syempre 3D yan, hindi yan squared, hindi yan siya circle lang, so sphere nga siya. So basically meron tong volume itong sphere na to. Hindi ko lang dito medyo maipakita sa inyo, but kasi pag nilagyan natin ng volume yan or weight, mawawala. So stick na lang tayo sa ganyan, but idea is ito ay meron siyang certain volume. So ito yung ating pinaka-figure, and then let's have the dimension. So sabi dito, inside a spherical balloon siya, and then the diameter is 20 cm. So kung lalagyan ko ng center dito, which is the center of the of our balloon, we could also say na itong portion dito, so let's have here yung red. So mula dito papunta doon sa dulo ng ating dikit yan ha. So dulo ng ating sphere, and of course ang ating cylinder is actually equal to 20 cm. So the diameter, which is capital kasi ito yung mas malaki, that's 20 cm. And then this problem requires us to find the dimension of the largest cylindrical can that can be placed inside. So pwede naman na ganito lang din kalaki. Syempre, pwede yung drawing nyo. Pero pag tinutukoy natin is pinakamalaki, so need kayong mag-drawing ng pinakamalaking cylindrical can. But you can also draw something like this kung halimbawa medyo napataba yung inyong can. So pwede rin ganyan. So ano kaya yung magiging perfect dyan na drawing if ever? Pero kahit naman ano yung drawing nyo, it just boils on the same fact na you're just assuming na ganito yung magiging tsura niya. Okay? So first things first, we know that the fixed things here, or the fixed values is isa lang pala siya, diameter of the spherical balloon. So this one is constant, and the variable that we need to determine is the dimension of the cylinder, which are the radius for our, or diameter. Let's just use diameter. So the diameter of our cylindrical can, and of course its height. Okay, so yun yung ating mga variables na need to be determined. So with that, if we need to find the dimension for that, and then we're talking about, in this case, volume, we know that the general equation that we have is simply pi r squared h. And if we want to represent this in terms of d, we could just simply use pi and then d over 2, because that's radius, and then squared height. So we're left with pi and then d squared over 4 and then times h. So this is our general equation for this expression, and then we need to express either h in terms of d or d in terms of h. So it could interchange depending on your perspective or what makes you comfortable. So in this case, I'll be deriving, or I'll be looking back at the figure just to have the relationship between D and H because kung mapapansin nyo, wala tayong direct relationship from the problem itself. But looking back at the figure, we could see right here na pwede nating i-chop yung portion na merong diagonal na, may diameter na dinrawing and then itong diameter ng cylinder and then yung height. This one is D, this one is H, and then this one is the capital D. And knowing na ito is right angle, we could just use the Pythagorean theorem. So by Pythagorean theorem, we know naman na D squared is equal to H squared plus D squared. Kasi kung kita-kita nyo naman, ito yung hypotenuse niya. So with this, we already obtained the relationship of D with H. It's just that if we represent H as D squared minus D squared, then we need to take the square root of that. So basically, itong H ito yung equivalent niya in terms of small d. Yung capital D, we don't have anything to do that because siya naman ay constant. So wala siyang magiging aberya dito pag nilagay natin kasi constant naman siya. So we move on by substituting this expression to our original equation. So from here, let's say V is equal to pi, and then V squared over 4. So I'll just be factoring this pi over 4. Pi over 4 and then D squared, and then we multiply this by H, which is the square root of capital D squared minus D squared. Okay? And then from here on out, I would perform the necessary steps, which is the first thing is we need to take the derivative in terms of the independent variable, which is D. So, okay, or we could just simply say V prime of D. That's why letter D is something always brings up confusion in representing this in Lagrange form, because as you can see here, this dV over dt is Leibniz form. So this dV over dt would really give you a headache of what does it really mean by this dd. But anyway, so let's just use this Lagrange notation. So that's V prime of D, and then this is equal to pi over 4. I'm just taking the derivative now. So these are two expressions in a product form. So we'll do product rule. So that is D squared times the derivative of this one. So that's 1/2. And then I have D squared minus D squared raised to negative 1/2. And then the derivative of what's inside is negative 2D, simply because this capital D squared is a constant. And then plus the square root of D squared minus D squared, and then we multiply that with the derivative, which is simply 2D. Okay? And then we move on with the process. So that's V prime of D plus from here on out, we know that we should equate this to 0. So this is 0 and then pi over 4, and then I'll go with simplifying these expressions first. So we cancel 2, and then negative, I'm left with negative D cubed divided by the square root of D squared minus D squared, and then plus 2D, the square root of capital D squared minus small d squared. Okay, and then of course this is equal to 0. So we could also simplify this by dividing this both sides by pi over 4, and our left with 0 is equal to this expression inside the bracket. So we could copy it from here, and then let me erase this. So this is now equal to 0. And then I will multiply both sides. I'll be multiplying both sides by the denominator. So as you can see here, that's capital D squared minus D squared, and then this one is the same. So this one becomes 0, that's 0, and then this will be cancelled out, and then this will be squared. So we have D cubed, negative D cubed, plus 2D times D squared minus small d squared, that is equal to 0. So we've already simplified this in a very short expression, and now we just have to distribute this further so that we can get the answer. So that's negative D cubed plus 2D D squared minus 2D cubed. that is equal to 0. And then when you add these two, we can get negative 3d cubed plus 2d d squared equals 0. Now I'll be factoring out positive d right here, so or negative d right here, so I can get a positive value right here. So that's 3d squared and then minus 2 capital D squared, that is equal to 0. Okay, and now the two values that I'll be getting from here will be negative d is equal to 0 and then 3d squared minus 2d squared is equal to 0. Now from this expression, let's use another color. So from this expression, we know that d is equal to 0. And then from this expression, we know that that's d squared, small d squared, is equal to 2d squared over 3, which gives us the value of the diameter in terms of the diameter of the sphere. That is simply equal to the square root of 2 over 3d. Okay, and we can also rationalize this expression so that we can get square root of 6 over 3d. So this is the expression of our answers. So in a choice between 0 and the square root of 6 over 3d, it is always practical to select this d because we're looking for the maximum dimension. And by just looking at this, we know already that this d equals 0 is the minimum of that expression, because we're knowing that the critical points actually give us values that can either be maximum or minimum. It gave us two values right here, and we know that if this is 0, we're basically talking about a dimension that is non-existent. I mean, the diameter is 0, so the figure is actually nowhere to be found. So basically, the minimum dimension can be 0 in a way that the minimum volume of a cylindrical can that can be fit inside here is simply no cylindrical can. But for the maximum, this is the value. So we'll be considering this as our solution and not this one. Okay, so knowing this dimension, we can go back to the expression of h, which is this one, and then we can now determine the other dimension. So in this case, we have the height of the cylinder that is equal to the square root of d squared minus d squared. And then plugging on those values, we have d squared capital, and then this d squared, from this expression, we could just write this as negative 2/3 d squared. So it simplifies your computation, and then this only means that you could just subtract this d squared minus 2/3 d squared, and that's just 3 over 3 minus 2/3, so that's square root of 1/3, and then we have d on the outside. So we can just also rationalize this into square root of 3 over 3d. Okay, so in this case, this is the expression of our d and h. In terms of the diameter of the sphere, we could get the maximum dimensions of the cylinder as square root of 6 over 3 and square root of 3 over 3 respectively. But we already have the diameter, which is 20 centimeters. So just to give you the final answer, we know that d of the cylinder is equal to square root of 6 over 3 times the diameter, which is 20. So d is equal to 20 over 3. So that's just 20 square root of 6 over 3 and then centimeter. And now for the height, we could just substitute d. So we have h is equal to square root of 3 over 3 times 20 centimeter. So the height is simply 20 square root of 3 over 3 centimeter. Okay, so these are the answers for this problem. So you already have the dimension of the cylinder that we need. So if you're asked to find the volume of the cylinder, you just have to apply the formula for your volume of the cylinder, and then you'll be able to get the answers for this. And you might be noticing that I didn't actually substituted d from this expression, kasi I could have used d here, 20 centimeter here instead of writing d, so that I will be getting a constant value instead of letter d. But you know very well that d is also a constant, so either way, if you substitute 20 right from the start or not, you'll just be getting the same answer. It's just that I didn't do that because I wanted you to see how it works when you don't have any value for the diameter. So in this case, this expression, where's that? This one, the one with the two check marks, that's the general expression wherein if you would want to inscribe a certain cylinder inside a sphere, then you would know that whatever the dimension of the sphere is for the diameter, it will always be expressed in terms of this expression. So even though the diameter is like, for example, that's just 15, 75 or any value, you'll just be using this expression to get the diameter and the height of the cylinder that can fit inside that sphere. Okay, so that's just for this problem. Now, it is easy because we're able to determine this Pythagorean theorem, but of course, in cases like different figures, for example, this becomes cone. So you won't be able to apply Pythagorean theorem because that's basically not possible in a right circular cone. So you just have to devise your own similarity or any property of the figure based on your drawing or illustration.